Welcome back to ROBT402, Robotic Mechatronic System Design, Lecture 3, Pneumatics, Actuators. Today's topics are as follows: Introduction to Pneumatics, Linear Actuators, Pneumatic Muscles, and Rotary Actuators. So basically we'll go through the different types of pneumatic actuators. Introduction to Pneumatics. What is pneumatics? Pneumatics in British pronunciation is pneumatic and American pronunciation is pneumatic. Word from Greek pneumatikos, from pneuma, which means wind or breeze. And pneumatic is the science and technology of pressurized air using piped, compressed air or similar gas such as nitrogen to transmit force and energy. So in different languages, you might pronounce it differently. In some languages, they pronounce P at the beginning, but in British and American pronunciation, that P is silent. 5 basic components of pneumatic circuits. A compressor, which makes air. A reservoir or receiver that stores air. One or more valves control air, so they control air or the movements of the air. A circuit moves air between the other components. An actuator or motor uses air to do something. So here we pressurize air, we produce that power, we reserve it here, we control it by valves, we transmit it by pipes and circuits, and finally we will reach to actuators to produce force and basically do some work. What are advantages of pneumatic circuits? First, availability. Air is everywhere. Transportable via pipes. So we could transport air or pressurize air via pipe. Storage. Compressed air could be stored. Low temperature sensitivity. So temperature could drop to a lower degrees. Incombustible. So the air is not combustible, so we could transmit it without being in hazard. Clean and environment friendly. So for any reason, if the air leaks to the air, we are not worried about the environmental cost. Lower cost compared to hydraulic components. So hydraulic components are usually bigger in size and cost. Why? Because pressure of hydraulic pipes are much more than pressure in air pipes. So that's why in pneumatic systems, we could use smaller size valve, we could use smaller size actuators, and we could use weaker pipes. Plus, we don't need oil, as we basically, it's essential in a hydraulic system, and we must have an oil or a liquid. But here, air is available everywhere and is free. High speed and acceleration actuators. That's why we should be careful once we are working around pneumatic actuators, because they move very fast with high acceleration and high safety on overload condition. So in case the cylinder goes under a heavy load or unexpected load, since the air is compressible inside the cylinder, so the cylinder will be compressed, and the damage is limited to the actuator, to the cylinder or the pipes, because they could accept some tolerances of pressurized air. So the air itself works as a compliant, as a spring, and that gives us a certain level of safety. What are the disadvantages of pneumatic systems? Air preparation cost. So anyway, that compressor should work once a while to prepare the pressurized air, and that costs of some money. Non-consistent speed due to compressibility. So that's true that compressibility brings us some level of safety, but from the other side, what is the trade-off? The trade-off is that the speed of those cylinders are not consistent. Why? Because anyway, the pressure inside a cylinder or actuator changes and is not exactly equal to the pressure on the storage or at the compressor. Limited force and the power transportation. So compared to the hydraulic system, the level of power transportation or the force, generated force, is much less, and we should be aware of this limitation. And noise pollution. Compressing air in the compressor creates sound. Plus, once the air valves works, or once the actuators work, we will see in coming lectures, there will be some exhaustion of the air to the atmosphere. So that creates some noise. Okay, so now we are familiar with the basics of pneumatics. At least we know the definition of pneumatics. Now we continue with the next topic, which is linear actuators. So linear actuators are basically the first pneumatic components that we are going to study. The first type of pneumatic actuators or linear pneumatic actuators are single acting cylinder. So what are these single acting cylinders? As you could see here in this animation, we have one main port. The high pressure air will be injected into the chamber of the cylinder, and that basically moves the piston forward. And we have a rod here attached to the piston, and we have also one spring. Once the pressure inside the chamber drops again to the atmosphere level, the spring will back the piston to the initial position. So now let's see the cross section of one single acting cylinder. Here we have a main port, and here we could see the piston, and the hole itself is the cylinder. So we have two chambers on the left side and one on the right side of the piston. On the left side, once we let the high pressurized air to come into the chamber, the piston will move forward and the spring will be compressed. You see here there is one small vent here to let the air inside the right chamber to be exhausted to the air. So without this small vent here, the piston moves forward but will stop because the pressure inside the right chamber will increase and then will be equal to the left side, and once we are in the equilibrium, the piston will stay somewhere between. So we need this vent to let the air to move freely in and out from atmosphere. Okay, so here you could see one educational sample of these single acting cylinders, and you see the main port here. By actually looking once at the cylinders, the way to identify between a single acting and double acting cylinders are finding the number of main ports. So on this one you could see that we have one main port, and we could see we could attach the pipe to this port. So this is a single acting cylinder. Or what is the other way? Looking at the symbol. All pneumatic components have a symbol. Once we start working with the Festofluid SIM software, we need to have we need to work with symbols to make our circuit. So here you see the port, the main port, plus the spring. So it's very clear that this specific cylinder is a single acting cylinder. You see some industrial samples here. Again, we need to either find the number of ports on the cylinder to identify the type of the cylinder, or the best is to find the symbol. So symbols are usually attached to a label on the shield of the cylinder, and the best is to try to find the symbol. You could watch this YouTube video for better understanding the concept of single acting cylinders. What are the main characteristics of single acting cylinders? Simple to control. Why? Because they only have one port, and we need to only pressurize or depressurize that port. They have complex mechanism. Why? Because they have one spring inside. So most of these characters are written in comparison with the double acting cylinders that we will study soon in the coming slides. So you may want to back and review these characteristics to better understand these characteristics compared to the double acting cylinder. They have safe home position, so it means that once the pressure air is out, and once the cylinder is detached from the compressor, the piston will back to the initial position. Why? Because we have a spring inside. So it always backs to the initial position because of the spring. Hard to repair, again, because of that spring. If something goes wrong with the spring, we need to open it up. And sometimes that spring is already compressed, and it needs special equipment and safety to open the cylinder. The example of that is the air brake of big trucks. Lack of full control. Why we don't have full control? Because again, we have one port, and we could only pressurize and depressurize one chamber. But on the other side, the control is simple. Non-consistent force. Why the force is not consistent? Because on one side, we have a pressurized air. On the other side, we have a spring. And that spring, the force of the spring is proportional to the travel distance of the spring. Or F is equal to the Kx, and K is the constant of the spring, or stiffness of the spring, and X is the distance from the free links. So the resultant force at the rod or at the output of the cylinder is not consistent, is not constant, and it depends on the position of the piston. Okay, so let's move on to the double acting cylinder. Very similar to similar mechanism. We have a cylinder, we have a piston, and a rod is attached to the piston. We have two chambers on the left side and on the right side. But we have two ports, so we could pressurize and depressurize each chamber. So to move the piston or the rod forward and backward to the left and right, we need to pressurize one chamber and depressurize the other. And if we want to move the opposite direction, we need to opposite the act. Pressurize the other chamber and depressurize the other one. So here you see one educational sample of these type of cylinders. Very clearly you could see two ports, two main ports. We don't have those vents because those ports or main ports act as a vent. Here you could see one industrial sample. Hard to see the ports here on this picture, but if you look at the part closely, you could easily identify those ports. And here we have a symbol. So clearly you could see two ports on the cylinder, but we don't have any spring inside. So mechanism itself is simpler because we don't have that spring. Okay, so what is the resultant force on these type of cylinders? On one side, so here we have a cross section. You see the right chamber and the left chamber, and the rod is attached to one side of the piston. Let's see when we pressurize this chamber and depressurize the other one and see what will happen. So we have a high pressure here on this side, so we have a pH, and we have a low pressure on this side, or we have a PL, and that low pressure is equal to the pressure of atmosphere, which is 1 bar or 100 kilopascal. Okay, so this is a cross-sectional area, or the effective or the applicable area of the pressurized air on this chamber. So F1, the force on the right side of the piston, is equal to the pH multiplied by A minus, and we have anyway we have a pressure here. It's not high pressure, but it's equal to the atmosphere pressure. So minus a PL, or low pressure, multiplied by A minus A0. Why we have A minus A0? This is the applicable area on the left side. So A0 is the cross-sectional area of the rod, and that should be deducted from the whole area. Okay, so pH multiplied by A minus PL multiplied by A minus A0, and we have a friction also between the piston and the walls of the cylinder. Now, let's basically do the opposite, or let's say we want to move the piston backward. So we need to pressurize a left chamber and depressurize the other one. So we have a high pressure on here on this side, and we have a low pressure on here. So force on this case will be equal to the pH multiplied by the applicable area, which is A minus A0, minus PL multiplied by A minus friction. So let's assume we have equal friction on both directions of or both course of a movement forward and backward. So F1 minus F2 is equal to the pH plus PL multiplied by A0, and that is bigger than 0. So what we want to understand here from all these calculations is that the force on moving forward and backward, forces on basically moving forward and backward are not equal. And plus, in some cases, when it comes to pneumatic valves, we see that in for some applications, we need to pressurize both chambers. And for those cases, the pressure on the left and right is equal, but the applicable area of the pressure is not equal. We expect to have a stationary piston, but the piston moves. So in this case, if we have a high pressure area on both sides, the cylinder will move backward because the applicable area on the right side is bigger than on the left side. Okay, so let's go to another type of pneumatic cylinders. Those are double acting, double rod cylinders, or also some cases they call it true rod. So very similar mechanism. We have two chamber, a piston. We have two main ports to pressurize the one chamber and depressurize the other one to move backward and forward. But the only difference is that the rod goes through the piston, or it's attached to both left and right. So we could apply force from both sides, from here and here. So this is one advantages in some cases. Plus, if we have equal pressure on both sides, then the piston will stay stationary because the applicable area of the pressure is equal for both cases. And here we have a double acting, double rod cylinder industrial example. On this one, you could easily identify two ports, and you see that we have two rods. So visually, in most cases, we could identify the mechanism of pneumatic actuators, but again, the best is to find the symbol on the label because the inside mechanism could be more complicated as it looks. Characteristics of double acting cylinders. They have more complex controls. So to control them, we need to have high pressure on one side and low pressure on the other side, and that brings us more complexity. So we need more complex or advanced valves. So when it comes to the pneumatic valves, we see that we need to use more complex valves compared to single acting cylinders. They have a simple mechanism compared to single acting cylinders because we don't have any spring inside. They don't have safe home position, so they don't back automatically to the initial position compared to the single acting cylinder because we don't have a spring. They are easy to repair because we don't have spring. We have full control on the movement because we could pressurize and depressurize each chamber. We have a consistent force, again, because we don't have that spring. And remember, the force of the spring is proportional to the position. But since we don't have that spring, the resultant force and applicable force will stay constant through all the course of the movement. Non-equal backward and forward force for the case of simple double acting cylinders, but the force, both backward and forward force, is equal for through rod double acting cylinders, and we should be aware of that, and equal backward and forward force for the extended rod or the through rod. Cylinder with the cushioning. So cushioning could be for both cases of double acting and single acting. On this animation, we have a double acting cylinder. We are pressurizing the left chamber, and we have low pressure or depressurizing the other one, and it moves forward and then backward. However, you see that the piston is not normal, and we have this bulge here. It's a kind of like extended piston, and it goes to these small chamber at the beginning and end. So that small chamber creates some cushioning. Why? Because the air itself is compressible, and the compressed air inside this small chamber at the beginning and end will deaccelerate the piston, and the piston mostly stops at the beginning and end. So without the cushioning, the piston could bang to the end walls, and of course it creates sound, plus it will decrease the life expectancy of these cylinders. So that's why it's good to have them. What is these small set screws here and the orifice here? So this orifice here basically helps us to adjust the degree of cushioning. So if we open it completely, this opening, the air could easily move from this vent outside and could be exhausted easily, and the level of cushioning will be very low. But if we close this orifice here and close this opening here, then the air needs more time to escape from these small chambers. You see the symbol here, so easily you could see those bulge on the piston, and that flash shows that the cushioning is adjustable itself. So here, let's look at the cross section of one cylinder with the cushioning. Here again, you see that this piston rod, or kind of like a bulge on the piston. Here we have this small chamber, and we have a cushion orifice here, and a set screw. This is a set screw. So again, once the piston reaches to the end, then basically this piston rod starts to penetrate into the chamber, and the air needs to escape from this small orifice. Okay, and that deaccelerate the piston and smoothly brings it to the end. What are characteristics of Cushing cylinders? More complex control, um, because the acceleration is not constant. More complex mechanism because of the cushioning compared to this compared to the regular double acting cylinder. Okay, hard to repair because we have more parts. We have the orifice, we have a set screw, and anyway there is a rod attached to the piston. Less impact force, so during its lifetime the impact force will be less and the life expectancy will be higher. A smooth force diagram at the end of the stroke. So force is constant, but when it comes to the ends of the stroke, then the force changes based on the cushioning level and opening of the set screw. We have less noise because we don't have that banging at the beginning and ends of the stroke, and we have adjustable cushioning in many of the cases. So symbols of Cushing cylinders. Here we could see a double acting cylinder. Why? Because we have two ports. Plus here you could see the cushioning here, but we have a cushioning on one side only. So on this end we have a cushioning, but not on this end because we don't have this rod or bulging here on the piston. On this one, the same type as the previous one, but is adjustable. We have a set screw that we could set the level of cushioning. This one, we have a cushioning on both sides on a forward and backward motion, and of course these are more preferable to the other one. It's always preferable to have cushioning because of the noise and because it will increase the life of those cylinders. Other types of pneumatic linear actuators are rodless cylinders. So in these cases, as it is clear from the name, we don't have any rod. The piston is connected to an external carriage. A mechanical or magnetic coupling system, we will see in coming slide. So we have, so here you could see the external carriage here, and this external carriage is attached to the internal piston by either mechanical or magnetic coupling. There no piston rod extends outside of the components, so there is no any rod attached to the piston. We have a piston inside. Okay, we have a piston. Without the piston, we cannot, of course, have a meaningful pneumatic cylinder. But the piston is attached to the external carriage, not a rod, and this carriage basically applies the force and do the work. Okay, so here you see the external carriage, and here you could see the cross-sectional area. We have a piston. On this case, we have a coupling, but this is a mechanical coupling between the piston and the carriage. Here we have one application. You see the carriage. See, this is the carriage. Here is moving across the cylinder, and another cylinder is attached to the carriage. Okay, so this one is two-dimensional Cartesian robot. One dimension and a second dimension is this one. So we have two actuator, two pneumatic actuator. The first one is this horizontal cylinder, which is a rodless cylinder, and the second one, which is a regular pneumatic cylinder, which has a rod and extends um, inward and outward. Another type of the coupling for these rodless linear actuators are those with the magnet couple. So we have the piston inside, we have a magnet, or the piston itself has magnetic properties, and the carriage also is magnet, and these two are coupled by the magnetic field. So here you could see one type of these pneumatic cylinders, and you could find it on a MPS 500 on the testing station for the elevator. So the elevator is a rodless cylinder, magnetic, with a magnetic couple. Here again, you see this magnet coupling moving forward and backward. They have a piston and we have external carriage, and you see the magnetic coupling between these two. But what is the mechanism of moving forward and backward? It's just pressurizing one chamber and depressurizing the other one, and vice versa, to move forward and backward. So basically we are moving the internal cylinder, and the internal cylinder then will move the external carriage. Okay, so symbols. Let's review some symbols. For single acting cylinders, again, we have one port and we have a spring. Have a double acting cylinders, two ports, don't have a spring. We have double acting cylinder because we have two ports and extended rod. And we have double-ended piston rodless cylinder. So we don't have rod here. Okay, we don't have any rod attached. And you see the magnetic coupling between the carriage and the piston. Okay, let's move on to other types of linear actuators or linear pneumatic actuators. Here on this slide, you could see multi-position cylinders. So what are multi-position cylinders? We have two cylinders back to back attached together, and each cylinder has two ports. So this one has 2 ports and this one has 2 ports. This one has its own piston and this one has its own piston. And we have a rod on this one and a rod on the other one. So what are possible positions? So if this chamber is pressurized and this chamber also is pressurized, both of them are moved completely backward to the end, and you see that this is one position for the rod. On this one, the first chamber on the left chamber of the first cylinder is pressurized, so it's moved forward, but the left side or the left chamber of the front cylinder is not pressurized, and the status of the ports remained as before. So you see the black one is the high pressure port, and the shallow arrow shows us a low pressure port. So you see that the status of pressure on the ports of the front cylinder hasn't changed, but for the back cylinder or the rear cylinder, the status of the ports has changed and switched. So this is the second position, and the last position is when we have high pressure on the left chambers of both cylinders. And you see on this case, we are on position 3. So what is the main advantages of these multi-position cylinders? As it is clear from the name, they are used to provide us multi-position, not only 2 positions. Again, you could see industrial applications of these type of cylinders, and the cross-sectional area of these type of cylinders, and 3 different positions. This one, and this one. Again, on the multi-position cylinders, we could see this cross-sectional area and different possible combination. Now it's clear that which chamber exactly is high pressurized and which chamber is has low pressure. And you see that we could move from position 1 to 2 and 3. The next type of pneumatic linear pneumatic actuators are tandem cylinders. Those are used for achieving high power. So in this case, you could see it's very similar to multi-position cylinders, but the only difference is that this rod here is coupled or tandem to the second piston. Okay, so this piston is attached to this rod. So once you have high pressure on both chamber, the resultant force will be add up, and we could have a higher resultant force at the output. Okay, so cylinder selection. How we could select our cylinder. How to select a cylinder based on required force and pressure. On this graph, which is a logarithmic graph, we have force on the horizontal axis and we have diameter of the piston on the vertical axis. Plus these lines shows us air pressure in bar. So for example, the pressure of the atmosphere, sorry, the pressure of the compressor is 2 bar, okay? So 2 times of the atmosphere pressure. Now, let's, for example, in one case, we need to have 1,000 force at the output of the cylinder, or at the rod, at the external rod of the cylinder. So then, based on the pressure of the compressor and the force at the output, we could find the proper diameter of the piston. So if we increase the diameter of the piston, of course, we could have a higher force at the output. But it will cost us some money, because bigger cylinder is more expensive. Plus, it occupies some space. So we need to have a proper diameter of cylinder to optimize the cost and space. Okay, so let's recap the linear actuators, pneumatic actuators, and pneumatic cylinders we studied. Pneumatic cylinders, we had single acting and pros and cons of them. We had double acting cylinders and their pros and cons. Comparison of single acting and double acting. Pneumatic cylinders, one type is extended rod double acting cylinders. We discussed the advantages of them. Pneumatic cylinders, cautioning, pros and cons. Rodless, we discussed different couplings of mechanical and magnetic coupling, pros and cons. And multi-positioning cylinders, pros and cons, and tandem ones. And finally, we try to discuss and understand the symbols of each type. Pneumatic muscles. So pneumatic muscles are a different type of pneumatic actuators. They are not linear pneumatic actuators, but they are one type of pneumatic actuators. As you could see, we have different muscles here. We have 2 ports. One type of muscles could have only 1 port. Okay, that's possible. But again, we need to pressurize and then depressurize that port, which needs special valve. Or we could close on these ones, we could close 1 port, okay, to have a simpler pneumatic muscles, and only pressurize the other side. You could see the symbol of them. On this case, you have 1 port, the other side is closed. So this is the basic type of pneumatic actuators and easier to be controlled. Here you see those are artificial muscles, so they call it artificial muscles. So the different sections, the casing, the elastic tube here, we have a thermal element, and we have a filler, and we have electric leading out wires. So these are the internal mechanical components of those muscles. But if we want to simplify the model, is nothing except kind of like a balloon, okay, some sort of balloon, okay. So let's see the differences in terms of generated force between a linear pneumatic actuators and muscles. Okay, so this one is muscle and this one is a linear pneumatic actuator. They're not equal in terms of generated force. So here on this graph, the x-axis or the horizontal axis shows us the percentage of the contraction. And the vertical axis shows us the generated force. First let's discuss the linear actuators. So this is the linear actuator. You see that the percentage, this gray area here, this gray area, the percentage of contraction does not have any effect on the generated force, specifically for the double acting cylinders. So the force remains constant, but is not the case for the pneumatic muscles. As you see, by increasing the percentage of the contraction, the level of the external force drops. Okay. Okay, so very similar also to the human muscle. Okay, so on the right side, you see a pneumatic actuator in function. The pressure divided by volume in these type of actuators are almost constant. So when the muscle is pressurized, could lift the object. So the thickness will increase, the height will increase, and the height will decrease, and that will lead to the work of lifting the object. The muscle could be modeled by a linear spring and damper, very similar to the human muscle. Here we have another type of pneumatic actuators. Those are blows actuators. The difference between these ones and the muscles are that when we pressurize a muscle, those could lift a part or object. But on these ones, when we pressurize, they could push the part. So very similar to the balloons, these ones, I could say. So they are used in clamping modules. As you could see, the symbol is very similar. We have these flexible plastic band at the top. These are the real applications and parts, industrial parts. So the chamber is pressurized, and the upper plastic band will be lifted to clamp a part and fix a part in place. So here we have these clamping modules. As you could see, they are used to fixate the part in place. So one of the advantages is that they could adjust themselves to the irregularities of the surface and inclination. So in this case, the clamping module has fixed the part, although the part doesn't have a normal, I could say, surface, or is not a rectangular shape part. And here we have two clamping module to fix this part in place, and again they could adjust themselves to the irregularities of the surface. Rotary actuators. So far we have discussed linear actuators and pneumatic muscles. Now we are moving to another section of pneumatic actuators, which is rotary actuators. Here on this slide, you could see different industrial application or types of rotary actuators. We'll go through the different types of these actuators in coming slides. So on this slide, I will discuss semi-rotary actuators with rack and pinion. The rack and pinion is used in different combination based on the internal mechanical structure of these actuators to convert a linear motion of pistons or pneumatic piston to a rotary motion at the rotor or the rack. So in this case, you could see one example that we have two piston and racks attached to the pinion, and that converts the linear motion to the rotary motion. On this one also a similar mechanism. We have two piston, rack and pinion. And on this one, instead of rack and pinion, they use a pulley and cable. Here we have one industrial application. You could see two ports, two pressurized, two chambers. And we have this rotary output which is attached to the pinion. Here we have again one type of semi-rotary actuator with rack and pinion. This is a symbol. You see we have this half circle that shows this is a semi-rotary. The range of motion is limited. It's not a full circular motion. And we have these triangles at each port that shows that these ports could be pressurized. So it means that we could either move clockwise or counterclockwise based on the pressure of each chamber. So usually these semi-rotary actuators should have two ports, and two ports should be able to be pressurized and depressurized. Otherwise, it cannot go back and forth. Another type of semi-rotary actuators are those with the vane cell. So here we have two chambers, and two chambers are divided by a blade and two ports. So when we pressurize this one, the blade moves counterclockwise and vice versa. You see that again the range of motion is limited. Again here we have those type with the vane cell, and they could have a different range of motion. And here this is the type exactly we have on MPS 500 on the swivel module on distribution station. So if you refer to those videos, you see that what exactly I'm referring to on the distribution station. So the swivel arms attached to the semi-rotary actuator to do the pick and place by the suction and rejection. Again, you could see the symbol, and here you could see two ports exactly, and this is a mechanical part is attached to I could say the vane, and is used to activate and deactivate micro switches at the beginning and the end of the motion. So when this mechanical parts comes into contact with the rollers of the micro switches, those micro switches will be activated. And here on the windshield of these big trucks and buses are used for the wipers, okay, on the windshield. Another type of rotary actuators are those ones with the unlimited range of motion. They have a different internal mechanism. This one, we are using multiple linear actuators and the crank. And on this one, we have multiple blades, very similar to those with vane cell. The difference is that on these ones, we have eccentricity, and these blades could move inward and outward, and there is a spring that adjusts their motion and the sealing between the wall and the blade. So why we have eccentricity? Because we want to decrease the pressure as we are moving forward and compare the pressure store energy to the kinetic energy. Okay, so let's review some symbols here for a rotary actuator, unlimited range of motion. On this one, we have rotation in one direction only because we could only pressurize one port and we don't have control on the other one because of this triangle again here. We have a fixed capacity. We cannot change, let's say, the speed or the output power. This one, we have full range of motion, rotation in one direction, and we have a variable capacity because of this arrow. And here on this one, we have rotation in both direction because of these two triangles that we have on two ports, and we have a variable capacity. And on this one, this is a semi-rotary actuator. We have a limited travel of motion, and we have a rotation on both directions. And it was the end of the session for pneumatic actuators.